We'll start, sir. Not a problem.
Yeah. So good evening and welcome all. I personally welcome our very beloved and very important teacher, guest lecturer for us today, Dr. Sudheesh. Is professor from Bangalore Medical College, and the last session he has covered the topics on research methodology, very basics, how to plan and conduct a study. And today we have requested him to take us very interesting and brief journey, precise journey of how to select our statistical analytic tool in order to successfully take our research work to a reasonable and logical conclusion. So I welcome you all students on behalf of RAISA DNB online academic activities. Today with us we have Sir Sudheesh, and dear students, make full use of this session. Thank you. Over to Dr. Sudheesh.
Thank you very much for your kind introduction, sir. And once again, good evening to all the students. Of course, it's a long day. I'm sure you'd be tired. Unfortunately, this is a kind of a situation where what do you say? You need to, though it's a little boring, I'll try to keep as minimally boring as possible. There are two things what I'm going to discuss in this talk today. One thing is to select the appropriate sample size, appropriate statistical tests, and how to represent the data. And once you are done with that, how to present it in a paper, whether it is in the form of a table, figure, chart, or what is the most appropriate thing. So these two things we'll be discussing. I'd like to ask, since this statistics is a little tight thing, I would like to actually finish up with the statistical work first, and the rest of the things we can think later if time permits. We can do that things. We can discuss regarding the presentation of data in the paper. So this is one of the topics which I had presented in our conference also recently in 2021. So what do you mean by data? So you like before going to this particular data, we can just quickly have a recap of what we discussed in the previous class. The previous class, first we decided about how to generate a research question. So the research question should contain PICOT criteria and also should satisfy FINER criteria. Now, what do you mean by PICOT? PICOT is population, I stands for intervention, C for comparator, O for outcome measure, and T for time, or a time during which the study is being done. So it should contain, the research question should contain all these details, and it should satisfy the FINER criteria. Now, what do you mean by FINER? FINER criteria means it is feasibility, whether it is feasible in your institute, is it interesting to the person who is going to read that particular topic, and is it novel, is it ethical, and is it relevant to the present day situation. So based on these, once your research question satisfies these things, then you can always go on and prepare a calculate a sample size. In that, based on so for calculating sample size, we require an effect. We should know what is the hypothesis. We should know what is the type of study, whether it is parallel design or it's a crossover design, and then whether it contains whether it's a null hypothesis or an alternate hypothesis. And once we know these things, what are the ingredients you should have? There are three assumptions to be made and three things we have to keep in mind. Things we have to keep in mind. So three assumptions to be made is, one is the effect size, and second thing is the variance, that is the standard deviation or dispersion of data, what is the anticipated dispersion of data, and finally the errors, that is the alpha and the beta errors, where we keep beta error at 20 and alpha error at 5 customarily. And then with this you incorporate the parameters into the formulae and you will get the adequate sample size. So when calculating sample size, two things we have to keep in mind is that when you calculate a sample size, you should always have the primary outcome measure in your mind, and your sample size should be based on the primary outcome measure. You decide a primary outcome measure and you quantify them, and then you assume the 4 parameters what I told, that is your effect size, your variance, your alpha and beta error, and you include these things into the formula, incorporate these things into the formula, and you get a sample size being calculated, and then you compensate, you add for dropout compensation, and final you'll get the final sample size. And once that is done, you describe the methodology, where you describe what is the place of study, what is the duration of study, and then it should also contain what the methodology in detail, like how do you exactly perform the study, and then what are there should be a clear cut mention of what all study tools and assessment tools you use. It might be BP operators, it might be a questionnaire chart, it can be a VAS score chart, anything. So they are all called as the assessment tools, and all those assessment tools should be clearly mentioned and clearly defined, and every parameter should be clearly defined with regards to your study. Every parameter has to be defined. For example, if you are talking about analgesia, you describe about what is the duration of analgesia, what do you mean by onset of analgesia, what do you mean by duration. Everything should be clearly defined in your study. So, and then of course, not to forget the inclusion and the exclusion criteria. It should be very clear. So this is regarding the methodology. And once you collect all these methodology from the one, you to conduct the study using this proper sound methodology, and then you collect certain certain numbers or certain values. These are nothing but termed as data. Data is nothing but individual pieces of factual information or a set of parameters recording during a research. It can be which is based upon the primary and the secondary objectives. And it's very important to understand that selection of a proper tool is critical for effective representation of data, and use of one of the most ideal method of data representation. The use of the most ideal method of data representation results in better understanding of the data. So data collection is most of the time based on the research question, as I told, PICOT criteria. And if you just imagine, if just come to the most basic terms. So whenever we do a study, we fill the pro forma will contain all these parameters, isn't it? Name, age, parity, department, indication, duration of surgery, uterotonics, etc. So these kind of various parameters you collect. These are nothing but termed as variables. These are the variables what you record during your study period. So, and they are entered in an Excel chart, and they are known as variables. Now coming to one of the most elementary thing you should understand is what are the types of variables you collect. You collect multiple types of variables. It might be gender distribution, it might be incidence of PONV, it might be binary variables such as PONV, yes or no. It might be grading of your ASA, like ASA 1, 2, 3, 4. Likewise, there are so many things so many data which you collect during the course of your study. However, not all data are similar. They are actually different. They are grouped under different types of, grouped under different subsets. And those subsets, now why do you want to group them under different subsets? That is because once you know what subset to belong to, you know exactly how to represent them in the, and how to describe them, and also how to use a proper statistical test for those kind of data. So variables are basically can be classified into quantitative or qualitative. Again, this qualitative data or categorical data are basically they are the ones which are not measurable by a quantity or a number, so or a integer. Basically, to be precise, it's an integer, not the number. So qualitative, basically they represent qualitative. For example, it can be a male and female. It can be ASA grade 1, 2, 3, 4. It can be PONV grade 1, 2, 3, 4. Or it can be cancer stage severity, grade, stage 1, stage 2, stage 3, stage 4. Anything like that. So basically they are all known as categorical, because they just describe the patient, where the patient falls into which category. So that's why they are known as categorical variables. Further, these categorical variables are classified into ordinal or nominal. Now, what do you mean by ordinal and nominal? Let us say nominal. Nominal means they are basically unordered categories. For example, if I say gender, see, gender, male and female, most of the time they are all equal. It's not like male is greater, female is lesser, or something like that. Male is also equal, female is also equal. So therefore, likewise, if you take an example of blood group. So blood group consists of AB, and O. All four are basically they're all of equal chance. It's not like A is better than B, B is greater than C, something like that. Likewise, treatment groups. Let us say you are grieving. Most of the studies, most of the times, we in the studies, what we do is group A received clonidine, group B received fentanyl. That's what we write. So they are also considered as nominal variables only. They both are nominal variables. Likewise, death, survival, all these things are considered nominal. Nominal means they are just represented by numbers which are of equal quality, equal respect, or equal strength. Now coming to on the other side, we have ordinal data. Ordinal data basically are classified or they are basically ordered or graded categories. For example, if you consider age, age can be child, adult, and elderly. Likewise, ASA, grade 1, 2, 3, 4 means this follows a particular order. Somebody, if you say somebody is ASA 1, you clearly understand that he is a healthy patient. And somebody says ASA 2, you clearly understand that this patient has got some comorbidities, but it is well controlled. So likewise, basically they explain the severity of the or the gravity of the situation. They grade the gravity of the situation. Likewise, cancer stages, cancer 1, 2, 3, 4, stage 1, stage 2, stage 3. This is actually an ordinal data. So the quantitative data, qualitative data, or categorical data are classified into ordinal or nominal. Ordinal means it follows a particular order, or it represents a particular order, whereas nominal doesn't represent a particular order, but rather it gives equal weightage to all the data. So that's about quantitative data. On the other hand, we have something called quantitative or numerical data. So these data are basically represented in the form of numericals or integers, and they are again further classified into discrete or continuous. Now, what do you mean by discrete? Discrete are the ones which are specific integers without having any decimals in place. For example, number of patients admitted in the for today, number of asthma attacks per year, number of hospital admissions per year, number of deaths in that particular area. So here you cannot mention number of patients admitted. You cannot mention that as 38.5, isn't it? It's either 38 or 39. So there is no in between numbers. So these kind of things are known as discrete data. For example, number of episodes of whenever we discuss about the incidence of hypotension. Incidence of hypotension, you say whether the incidence was 1 or 2 or 3. You can never mention incidence as 2.5, 3.5, and something like that, isn't it? Like, so they are known as discrete data. On the other hand, we have continuous data, where these continuous data are called so because there is a possibility of existing the possibility of a existence of a continuum between two numbers. Let us say, suppose some in an example, we'll just for this, the example is age, height, weight, etc. Now, suppose if I talk about age, somebody can be 37 years, somebody can be 38 years, but somebody can be 37 years, 1 day, 1 hour. Somebody can be 38 years, 1 month, 1 week, 1 day, 1 hour. So what's your age on today? My age on today is 38 years, 1 month, or 38 years, 29 days. So there is always a possibility of a continuum being existed. Though that's why we mention age in completed years. We don't say age on as on date today. Okay, we mentioned age in years, completed years. Likewise, BMI. As I told, BMI can be 24, 24.1, 24.2, 24.3. Between 24 and 25, it can always exist in the form of decimals as well. So there is always a continuum of numbers, which is a possibility. It's a real possibility. So that is why these kind of data are known as continuous data. Now, why do you want to classify them as this kind of categorical or continuous data? It has got implication. That is because if you classify it like this, only then you can represent them appropriately in the during the description of the data, and you can use and the statistic test also varies depending upon the type of variable, which I am going to discuss in the subsequent tests. So as I told, the data can be represented in the form of a central tendency. Whenever we represent data, there are two things we represent. One is the central point and the dispersion or the variance. So, now let us now to understand that what do you mean by a central point. The central point is nothing but the point which represents the center of the whole set of data. Let us say for example, you are collecting a data of age of 30 patients. So age, let us say it goes like this: 18, 25, 23, 24, 23, 21, 22, like that. So the entire 30 patients age goes like that. So when you mean by measure of central tendency, you are actually representing, you cannot write the entire value in the case, in the publication or in the table or wherever it is. All that you can do is you can summarize the set all these values into a single number, and this single number preferably has to be the it should represent the center of the entire set of numbers, and this value is known as a measure of central tendency. Generally the central measure of central tendency in our clinical statistics is either mean, median, or most of the time we do document the data in the form of mean and median and not mode. So it can be, so this is the measure of central tendency. Likewise, we have something called measures of dispersion. Now, what do you mean by measures of dispersion? Measure of dispersion is the measure which tells how far a one particular value can be from the measure, from the central value. For example, let us say somebody says standard deviation. Let us say we'll put an example: age of a patient, age of this set of patients is 37 plus or minus 2.5. So what does this mean? Here, the measure of the central tendency is 37 and the measure of dispersion is 2.5. It means that the values, 67% of the values lie between now 37 minus 2.5 and 37 plus 2.5. 37 minus 2.5 is 34.5 and 37 plus 2.5 is 39.5. So more 67% of the values of this particular set of patients lies between 34 and 39 is what is explained by the measure of dispersion. It tells how far the values move away from the, how far a particular value can move away from the central value. So this is represented in the form of a standard deviation, variance, range, or interquartile range, depending upon what kind of data you represent. Normally, whenever I was just discussing about this distribution of data. Now, why this distribution of data comes is because of this variance, because not all humans are same. Not all humans will have a same value. Invariably, there is always a deviation of a value away from the midline, depending in each patient. And this distribution, this movement of this data is known as the distribution of data. Categorical or nominal data generally shows binomial distribution. They generally show binomial distribution only, whereas quantitative data may have normal or non-normal distribution. So binomial or normal distribution, categorical data doesn't show any other distribution. Most of the time it is binomial distribution or normal distribution, whereas quantitative and continuous data may have normal or non-normal distribution. What do you mean by normal or non-normal distribution? Normal or non-normal distribution is, that means if you plot all the data on a graph, if a data has got a normal distribution, it generates a bell-shaped curve. If it doesn't have a normal distribution, it has got a different shaped curve, which I'm going to show in the subsequent slides. Now, why is it this important? Why this understanding of quantitative and quantitative, why this concept of normal and non-normal distribution is important? That is because based on this only, you will understand what kind of, how it has to be represented, whether it has to be represented by mean or median. And also the application of statistical tests also depends upon whether the data is normally distributed or non-normally distributed. So that is the importance of understanding this normal distribution of data. So this is what is normal distribution, as I was telling. So if you see, if you plot all the values, let us say you collected the age of around 30 patients and you marked them against the numbers. Let us say this is the age and this is the numbers. So they actually form a proper Gaussian curve. This kind of, or a bell-shaped curve. When you just plot the edges, it will form a bell-shaped Gaussian curve. And this kind of, when they form this kind of a Gaussian shape, bell-shaped curve, it is considered as normal distribution. And in this, the mean, median, and mode lie in the center of the bell-shaped curve. That is the importance of normal distribution. They are symmetric bell-shaped, and the mean, median, and mode occupy the center. And the measure of dispersion is represented by the standard deviation in this normal distribution. So, and to further, one standard deviation from the mean represents 68% of the observations. Let us say the mean is here. From here to here, one is representing the one standard deviation, and this, within these, 67% of our observations, whatever we collected in our data from our study, will fall in within this range only. And two standard deviations, the 95% of the values will fall in this. That's how it gives. So larger the standard deviation, flatter will be the curve. Next, we'll move on to non-normal distribution. Here, the values deviate to one side. Data is not normally uniformly distributed on either side of the mean. For example, something like this. The data can be moved to one side of the mean or the other side of the mean. When it is moved to one side of the mean, it is known as negative skew, that is skew to the left. When the, see, if you see, the mean is somewhere here, but the data is moved to the left side of the screen. So the data is, this is known as skew to left. Likewise, if the data is moved to the right, sorry, the data is moved to the right, it is skewed to the right. So when I say right and left, it's not in front of me, but along the screen. It's the right of the screen and the left of the screen. Now, once we understood that there is always a distribution of data, whether it is normal distribution or non-normal distribution, we know that the values move away. Now, how to quantify that movement? There are two parameters which are used in our statistical language. They are known as the skewness and the kurtosis. So, what does this skewness mean? Skewness is the measure of asymmetry and a deviation from a normal distribution. It just tells how much a value has got a tendency to deviate from the normal distribution, whether the tendency is too high or tendency is too low. A value of skewness varies between more than 0 or less than 0. Less than 0 being negative skewness, more than 0 being positive skewness. Suppose if a value is less than 0, that if the skewness is negative, that means the median can be more than mean. Positive skewness means a value more than 0 and this median is less than mean. In general, a skewness of more than +1 or less than -1 is taken as significant deviation from normal distribution, and it indicates that the data is not normally distributed. So this is the take home message. A skewness of more than +1 or less than -1 is considered as non-normal distribution. Now, where do you get this value of skewness and not? So if I just go through the previous slide, see, this is just, I just picked up from one of the SPSS software. See, when you put all the values in SPSS software, it will give all these values. Did you see? It gives mean, it gives median, it gives standard deviation, it gives skewness, it gives kurtosis, it gives all these things. So in that, now, at least now you understand by seeing the skewness. Now in this case, if you see the skewness is 0.2. So if you go back to the previous, just now what I told was a value of more than 0, that is more than plus 0.1, indicates the skewness is more. It is non-normal distributed. But if you see the skewness here is 0.21, which means the value is lying between 0 and +1. So therefore, it is not a significantly non-normal distribution. It is a normal distribution. And it is again represented here. If you see, the mean and median both are 15.5. It is further supplement. So therefore, a skewness is less than 1. It indicates that the value is normally distributed. The values are normally distributed, and it is also objectively proved by seeing the mean and median, which is also equal. And also next is the next parameter is the kurtosis. What do you mean by kurtosis? Kurtosis is the measure of peakedness of the probability of the probability, and it gives information about the tail of the curve. Positive kurtosis means it has got a tall peak and fat tails. Okay. Whereas negative kurtosis means it has got a flat peak and a small tail. Now, what do you mean by these things? I'll just explain you in the next picture, as you see. And the kurtosis of a normally distributed data by convention, the value of 3 is considered as a normally distributed data. So I was just talking about the kurtosis value. See here, the kurtosis value is here 4.2. Normally, I told normally the value is 3. Now it is more than 3. That means it has got a tall peak, and if you see, it has got a thick fat tail. So this is normally distributed. Whereas a kurtosis value of minus 1.2, if you see here, it has got a flat peak. It doesn't have a tall peak, and it has got no tails at all. So it indicates that the data is not normally distributed. So now finally, so as I told, there are various methods of understanding whether the data is distributed normally or not. So we just talked about the importance of skewness and the kurtosis. What are the other ways? I think that is very difficult to follow all those things. So sometimes we might have to do some simple measures to understand the data distribution. One of the most simplest things is histogram. So if you see, you just mark the, first you collect all the data, you put them into class intervals. For example, let us say you collect the data of 30 patients. I told 15 to 20, 20 to 25, 25 to 30, you make such small class intervals and see how many patients fall in each category. And with that, you mark a histogram and you join the points like this. If they form a bell-shaped curve, that means the value is normally distributed. If they don't form a bell-shaped curve, that is non-normally distributed. That's the simplest and crudest way of doing a distribution check. Other than that, next I told you, as I told you, calculated values of skewness and kurtosis, value of more than 1 or less than -1. Likewise, kurtosis values of more than in excess of 3 or less than 3 is considered as non-normal distribution. Finally, if these things are not helping, then we go to apply certain tests of normality. Now, what are they? They are known as fit to goodness chi-square testing. So, among them, the most commonly used tests are Shapiro-Wilk and Kolmogorov-Smirnov test. So, now what is the significance of this? I'll just summarize the entire thing. If you collect a data, quantitative data, let us say BP, your SBP, DBP, MAP, all those values, or duration of analgesia in hours, or onset of analgesia in minutes. You might collect all these data. You don't know, these are nothing but they are the quantitative data, isn't it? So they are the quantitative data. You don't know whether these quantitative data are normally distributed or non-normally distributed. To understand whether they're normally distributed or not normally distributed, you take all these values and apply Shapiro-Wilk test or Kolmogorov-Smirnov test to these values, and you will get a p-value. That p-value, if it is less than 5.5, you consider this thing is to be normally distributed. If it is more than 0.05, it is less than 0.05 is considered as skewed distribution. More than 0.05 is considered as normal distribution. But however, they are very sensitive to sample size, so that has to be kept in mind. Now, once you understand whether the sample size is normally distributed or non-normally distributed, what you do further? If the data is normally distributed, so you take the continuous data, apply this statistical test of normal distribution. If the tests say that the data is normally distributed, you straight away go for parametric test. What are these parametric tests? I'm going to describe in the subsequent slides. If the data doesn't show normal distribution, if they show skewed distribution, by applying many of these statistical tools to assess the normal distribution, if they say that it is not normally distributed, then you can apply certain, you can do certain maneuvers to make them normal, like logarithmic transmission, etc. I don't want you to keep, break your head on all those things. You just tell the statistician to transform to normality, make an attempt to transfer to normality. Once they do a transform to normality, if they those transform data show normal distribution, then again you can apply parametric test. if it doesn't, in spite of this manipulation, it doesn't show normal distribution, then you can go for non-parametric test. Now, what are these parametric and non-parametric tests? As I told, whenever there is a Gaussian distribution, we represent that as mean and standard deviation. If there is non-Gaussian distribution, we represent in the form of median and interquartile range. This is the thing why we want to know whether the data is normally distributed or non-normally distributed. Normally distributed data, we represent the data as mean and standard deviation. If it is not normally distributed, we represent it as median and interquartile range. So just we'll take a small example here. This is a randomized control trial for comparing two popliteal and catheter tip position for postoperative analysis after day case surgery of hallucis valgus repair. So the baseline characteristics, age in years. Now, what kind of data is this? Normal. What kind of data is it? Is it continuous data, or is it a quantitative data or a qualitative data? Categorical data. Age is a quantitative data, and it is a quantitative, discrete or continuous. It is continuous data. It's a continuous quantitative data. Next, gender, 36 and 33. So what kind of data is this? It is categorical data, because it has got only two categories, isn't it? Male or female. There is nothing called in between or anything. So therefore, it is categorical data. It is nominal data, nominal categorical data. Likewise, we have other two parameters, that is height and weight. They are what kind of data? They are all quantitative continuous data. So therefore, how are they represented as? See, in case of age, it's a quantitative continuous. So it is represented in the form of mean and standard deviation. Whereas the gender distribution, male and female, is represent, they are basically categorical binomial data, and they are represented in the form of frequencies. Likewise, if you see, this is the NRS score, that is a pain score at the end of 4 hours, at the end of discharge, at the end of 24 hours, etc. They are represented by a number and a range. So they are actually median and interquartile range. Now, why are they represented this way? That is because the values have showed skewed distribution, non-normal distribution. That's why they are represented in the form of mean and interquartile range. So with this background, now you understood how the data has to be represented. Suppose if it is age, you represent in the form of frequencies. If it is age, gender, etc. If they are non-age, height, weight, NRS score, or duration of anesthesia, all those things are continuous variables, continuous quantitative variables, and they are represented in the form of mean and standard deviation or median and interquartile range, based on whether they are distributed normally or they show skewed distribution. So that is about your data representation or descriptive statistics. Now, once you describe the data, you apply various tests. Now, how do you know how to apply? How do you know what test to be applied? So this is an important slide which you have to concentrate. Okay, as I told earlier, there are parametric and non-parametric tests. So parametric tests are usually applied when the data is normally distributed, and non-parametric data are applied when it is not normally distributed. Okay, so let us assume we are doing a study comparing the two different groups. Okay, so we are comparing two different groups, that is A and B, and they are normally distributed. The data is normally distributed, quantitative data. So what test you apply? If it is unrelated, that means when you are comparing between the groups, let us say you are comparing the age between group A and group B. So they are unrelated. They are known as unrelated data, and you apply students T test. Students T test. Okay. Suppose if you are comparing the, let us say another example where you are comparing the blood pressure at baseline at 5th minute and 5th minute. Let us say comparing BP before and after intervention. Let us say you gave lignocaine IV for pressure response. You want to compare before and after administration of lignocaine. So these kind of data are known as paired data. They are known as related data, and the test applied for that is pair T test. So I repeat, when there are only two groups, you are comparing between two groups, you apply students T test when when you are comparing group A versus group B. Within group A itself, if you are comparing 5th and 10th minute reading, or 5th and 10th baseline and 5th minute reading, you apply pair T test. So that is the simple way, as simple in the simplest way you can understand. Suppose if the data is not normally distributed, if the number of groups is more than 2, let us say you are comparing clonidine, dexmedetomidine and control, okay, and the data is unrelated, you apply one way ANOVA. That is, when you compare group A versus group B versus group C, you apply one way ANOVA. If the data is related, that means if you are comparing baseline with 5, 10 and 15 minutes reading, that is known as related data, and that time you apply repeated measures ANOVA test. Anyways, it's not mandatory to remember all these things, but it's just important to understand that whenever there is a normal distribution, two groups, you apply student T test and pair T test. If it is more than two groups, you apply one way ANOVA test or repeated measures ANOVA test. Likewise, now this is when the data is normally distributed. Let us now see if the data is not normally distributed, what will happen. If the data is not normally distributed, you are comparing two groups and the data is not normally distributed. So if the data is unrelated, let us, for example, you are comparing group A and group B, you apply Wilcoxon-Ransom test or Mann-Whitney U test. Okay. And if they are related, as I told, 0 minute baseline and 5th minute and 10th minute, like that, if you are comparing, you compare using Wilcoxon sign rank test. Suppose if you have more than two groups with a non-normal distribution or skewed distribution, you go for Kruskal-Wallis test if they are unrelated. I mean, group A versus group B versus group C, group A versus group B versus group C, it is non-normal distribution. You apply Kruskal-Wallis. If they are related variables, like for example, within group A only, 0, 5, 10, 15 minutes comparison, you apply Friedman's test. So again, non-parametric test, you apply Mann-Whitney, Wilcoxon sign rank, Kruskal-Wallis and Friedman. So whereas one way ANOVA repeated measures ANOVA in case of parametric, normally distributed data. So to understand that better, we'll do certain small examples. This is a study which is trying to study the effect of duration of analgesia with addition of 150 micrograms of clonidine intrathecally along with bupivacaine in a patient undergoing total knee arthroplasty. Okay. Total knee arthroplasty. So what they did, they collected two groups of 50 patients. In control group, they gave hyperbaric bupivacaine with saline, whereas in group B, clonidine group, they gave bupivacaine with 150 micrograms of clonidine. And their outcome measure, primary outcome was duration of analgesia, secondary outcome was duration of sensory block and motor block. And these were the observations. Sorry for that slide. Yes. So these were the control group and clonidine group. So let us analyze one by one. What is age in years? Now age in years is represented in the form of what kind of data is it? It is continuous quantitative data, isn't it? Continuous quantitative variable. That's why they represent in the form of mean and standard deviation. Okay. Likewise, say these blue things, that is the sex and the ASA physical status, they are basically categorical variables, and they are represented as frequencies and numbers. Okay. So the age, weight, BMI, duration of surgery, they are all continuous variables and represented by mean and standard deviation, whereas gender and ASA physical status are basically represented as, they are categorical variables represented as numbers. Okay, this is nominal variable, this is ordinal variable. Okay, so this is about the variables. Now let us say what test we have to apply. See here, we are comparing two groups, right? We are comparing group A versus group B, isn't it? So they are unrelated to each other, and they are here the data is represented in the form of mean and standard deviation. What does it mean? It means that the data is normally distributed. So you are comparing unrelated, you are comparing two groups which are unrelated and they are normally distributed. So what kind of test you apply? You apply students t test. Okay, suppose if this was represented by median, then it means that the data is not normally distributed. So that means median and interquartile range, if it was represented by median and interquartile range, two groups unrelated non-normal distribution, you apply Mann-Whitney U test. Okay, now coming to categorical, that is your gender distribution and the ASA physical status, they are usually checked by chi-square test. Okay, they are checked by, they are tested by chi-square test. They are tested by chi-square test. Now we'll move on to the one more example. Here, the effect of duration of analgesia with addition of clonidine 150 mics or 25 mics dexmedetomidine intrathecally to hyperbaric bupivacaine. It's a for TKR. This is a prospective randomized double study. Again, as I told, there are three groups. Group 1 control group which receives only bupivacaine. Group clonidine which receives group B which receives clonidine, group C which receives dexmedetomidine. So there are three groups. Okay. So this is the table of these three things. So let us start with categorical variables, gender distribution as well as ASA physical status, isn't it? So they are categorical, they are more than two groups. So, and they are unrelated. So therefore, whether they are normally distributed, most of the time these are binomial distribution. So you apply chi-square test. So for simple thing is, for all categorical variables, whatever it has to be represented in the form of numbers and frequencies, and it is tested using chi-square test. So one thing you take home point is, for all most of the 99% of the times when you look for categorical data or discrete data, they are compared using chi-square test. Only this continuous data. Now, in this continuous data, we'll move on. Now with this, we have done with the categorical data. We'll move on to the continuous data. So in the continuous data, we have age, weight, height, BMI, duration of surgery. Here, how many groups are there? There are more than two groups. Yes, number one. Second thing is whether they are normally distributed or non-normally distributed. All these things are mean and standard deviation. So therefore, we assume that they are normally distributed. So there are more than two groups. We are comparing group A versus group B versus group C. So therefore, it's unrelated. So it is more than two groups, unrelated, and it is represented by mean and standard. So therefore, it is normal distribution. So what test you apply? You apply one-way ANOVA test. Suppose if the data is not normally distributed, you apply Kruskal-Wallis test. I hope this gives much more clarity with regards to how the test have to be applied. So whenever we describe about a statistical approach, we have two things. One is descriptive statistics and inferential statistics. Descriptive statistics describes how your data is described, whereas inferential applies various statistical test tools to draw inferences from that descriptive data. So we have two concepts of inferential statistics. One is p-value and using point estimation, hypothesis testing and point estimation. What is the significance of this? P-value or a probability value is a number describing how likely is that your data would have occurred by random chance. I mean, how what is the probability of a null hypothesis being true in your study? That means, let us say if a p-value of 0.05 less than 0.05, what does it mean? It simply means that the chances of the result, let us say you group A had a value of 250, group B had a value of 280, and the p-value of 0.043. What does it mean? It simply means that if your test is done 100 times, the chances of the values of group A and group B being close to each other is only, now this showing around the difference of 30, isn't it? 250 and 280. The chances of this difference being equal, that is 250 and 255, is less than 0.043%. That's what the p-value means. It simply means that what is the probability of the values, what is the probability of a null hypothesis, and what is the probability of a alpha error of your study. It is unrelated to the truth or falsity of the alternative hypothesis, and it can accept or fail to accept a null hypothesis. The possibility, that's what, as I told, the duration of analysis of group A is 254 and the other group is, and the p-value is 0.002. It means the possibility of occurrence, this difference of these values by random chance and not by intervention is just 2 in 1 lakh. In remaining rest of the patient, it's actually due to intervention only. That means your intervention is more effective, not the casual thing. That's what the p-value says. What are the limitations of p-value? It doesn't permit any direct statement about the direction of the size of a difference or the relative risk between the two groups. And small studies may often report non-significance even when there are important real effects which otherwise a large study would have detected. So therefore, it is highly sample size dependent. So, and statistical significance, finally but not least, statistical significance does not necessarily mean that it's a clinically significant observation. Sometimes the values might be statistically significant, but it fails to imply or show the clinical significance. Just as this in example, see, the mean EtCO2 in a study was group A was 34 plus or minus 11.2, 1.12, whereas in group B 38.12 plus or minus 2.11. The p-value is less than 0.05, but so it shows it is statistically significant. But do you think a value of 34 and 38 is significant? A value of 4 mm of HA is EtCO2 difference, is it significant? No, isn't it? As long as they are lying within the normal range, it's not going to be significant, clinically significant. That's what I mean to say. So how to overcome this limitation? The best thing is effect size estimation and reporting and confidence interval reporting. Effect size and its important. The effect size is the quantitative measure of the magnitude of experimental effect. So a significant p-value tells us an intervention works, whereas an effect size tells how much it works, or what is the degree of, what is the extent to which the difference can exist. So this is represented in the form of Cohen's d, odds ratio, relative risk, Pearson's R correlation, R2 coefficient, or R2 coefficient of determination. These are various parameters which are seen when you apply a statistical test. You need not buy that, but you just keep in mind that it represents the effect size. So how do you calculate the effect size? Effect size is nothing but the difference between the difference between the control and the experimental group, which is divided by standard deviation. A significant p-value tells us that an intervention works, whereas an effect size tells us how much it works. Likewise, now how does this effect size really matter? If the effect size is small, that is around 0.2, it means that 58% of the patient of control group can be less than below the mean of the experimental group. If the effect size is 0.5, it means 69% of the control group is below the mean of the experimental group. If the effect size is large, it means 79 to 80% of the patients in the control group are below the mean of the experimental group. Let us say you are done a study on duration of anesthesia. Group A has got a duration of 400 minutes, whereas Group D has got a duration of 800 minutes. That means if the effect size is 0.2, 58% of the patients have their 58% of the patients in control group have their mean value less than 800, whereas remaining 42% still can have their value more than mean of more than 800. That's what it means. Okay. Effect size is usually used to quantitatively compare the results of studies done in different settings, as in meta-analysis. Coming to confidence interval, the next parameter, it's a range of values for a variable of interest constructed so that this range has a specified probability, including the true value of the variable. That means, for example, the endpoints of the confidence interval is the confidence limits, conventionally set at, and it is usually set at 95%. So, in other words, to simply put it, it's just that you are representing 95% confidence interval of a data set. What does it mean? When you say 95% confidence interval, it means, and you get a value range. Let us say 95% confidence interval of this duration of analysis is 200 to 800. What does it mean? It just simply means that when you do a study 100 times in 100 different populations of patients with the same protocol and with the same methodology, 95% of the times, the mean of the parameters are going to lie between 200 to 800. That's what it means. Only 5%, only 5 times out of 100, the value can lie either less than 200 or more than 800. That's what it means by 95% confidence interval. It gives an idea about the range of the observed effect size and shows the largest and smallest effects that are likely to take place. Values reflecting no effect enclosed in CI are classified and statistically insignificant, and values affecting are statistically significant, which are not enclosed in CI are statistically significant. Just to show an example, this is one of the study where we try to compare the NR ratio, neutrophil lymphocyte ratio with GA and spinal anesthesia. You see, at the end of 2 hours, what we have mentioned is here is this is the mean, this is the mean. Okay. If you see the values here, 2.24, this is the 95% confidence interval of this mean and standard deviation. Okay, this one 2.24 to 3.17, 2.5 to 3.25. Now, what is the significance of this? I just on a scale, if I mark these values 2.24 to 3.17, see 2.24 to 3.17, right? Likewise, I mark this one 2.58 to 2.58 to 3.21, 2.58 to 3.25. If you see, there is overlap between these two values. There is an overlap between those two bars. That means when the values are overlapping, the chances of statistically being significant is very less. Even if it is statistically significant, it's not going to be scientifically relevant. Likewise, I'll move to the next one. At the end of 2 hours, if you see the median with the 95% confidence interval, the 95% confidence interval was 5.51 and 10.75, whereas here 2.7 to 4.16. Again, I mark this on the scale 5.51 to 10.75. See, this is represented by this one. Likewise, the other one is 2.75 to 4.16. If you see, they are miles apart and there is no overlap between these two. So this is the one that if you do this study 100 times, 95% of the times, this is going to be statistically and clinically significant. So that's how, when they are not overlapping in the 95% confidence intervals of the two groups are not overlapping, that means they are statistically and clinically relevant and significant as well. The width of the confidence interval also tells how big or how small the true effect might possibly be, and hence, if you see the example, duration of analysis here, the width is 65, 256 to 325. If you see the difference, it's only 65. So the width of the CI is narrow, whereas in this, in another study, 286 to 254, the width is 550. So it is quite wide. So therefore, the possibility of heterogeneity is very high in this, whereas heterogeneity is very less here, or the outliers are narrow the confidence interval. Outliers are ruled out by the study itself. So the thing is, understanding data distribution is important to apply appropriate statistical methods, and hypothesis testing using a p-value is by now whether yes or no, and hence more clear. Whereas drawing conclusion in a target population based on a single value from sample can be misleading. Effect size is an estimate of magnitude of difference between the two groups, and confidence interval provides strength and direction of the effect, and statistical significance can be drawn in a better way based on 95% confidence interval than p-value alone. Statistical significance must always be distinguished from the medical relevance or biological importance. Thank you. So now, till now, we understood how to apply statistical tests. In the next another 15 minutes or so, I will quickly rush through how you represent your data. So data, as I told, it is based on we collect based on the time frame. This is the data what we collect, variables, and they're again classified into nominal, ordinal, categorical, numerical, or categorical, again which are again classified into ordinal, nominal, discrete, and continuous respectively. Okay. Before we proceed with statistical analysis, there are certain 3 steps, important steps what you need to carry out. One is the data cleaning process, where reconciliation, you cross verify the data entry by comparing it with your pro forma. Sometimes what happens is, instead of entering 69, you would have entered 669. So invariably what happens, that kind of typing error can grossly deviate your observed means and standard deviations, and it can result in erroneous results. So that's it's always better to cross verify your Excel sheet with your pro forma always, and also check for duplicate entries and find the missing data, and also detect if there is an outlier. Suppose if most of the values are between 20 and 30 and suddenly one value is around 60, that means it is going to seriously affect the direction of the data movement, and therefore such outliers are to be recognized, and you should not remove that, but rather you acknowledge that there were some outliers which has resulted in deviation of your values so widely. So data can be represented once you have calculated statistics. You can either represent in the form of text, or in the form of tables, or in the form of graphs. So which is the best way to present data? There is no single rule, simply. It all depends on the mode of data collection, its place in research question, whether it's a primary research, it's a primary outcome measure or a secondary outcome measure, and what is the information that has to be emphasized in this. And also, last but not the least, you have to go through the author's instruction journal for more details. Coming to text presentation, this is one of the most common. It's a main method of conveying information. You just go on writing in a running paragraph. Like for example, the number of patients in group A was so and so, group B was so and so, etc., etc. You go on writing that in the textual matter. So it's a main method of conveying information, and it can explain. It can be used to explain results, trends, and provide contextual information. And it also helps in detailed elaboration of tables and figures. And it's one of the best ways to represent the data if the data contains only 1 or 2 numbers. If the numbers is more than, let us say, if you are trying to imagine you are writing, you have recorded BP at 5, 10, 15, 20, 25, 30 minutes. You think, is it good to write in the form of a text where you mentioned the group A, the BP at 5th minute was this one, at 10th minute was this one? It becomes a long sentence, isn't it? It becomes a long and boring sentence. Instead of that, you represent that in the form of a table, it looks much better. So you cannot, so you can represent the text with the data by text only if the numbers are limited. Something like this. Overall success rates of a direct laryngoscopy was 99%, whereas with light scope it was 96%. It's simple, see. The disadvantage is it occupies more space, long reading time to read, and also inability to assimilate the full information when the large information have to be provided. So that is why you move on to either tabular or graphical representation. So during the tabular representation is the best compact way to present large volume of data, where precise mention of data is possible. For example, if you want to mention in the form of integers or in the form of decimals, etc., and multiple data can be represented in the form of in a concise manner, be it whether quantitative or qualitative data. See, the entire thing is represented. in the form of a single table. You see the age, duration, BMI, even gender, everything represented in one table. The entire demographic parameters, instead of writing one full big paragraph, if you represent in the form of one table, it is self-explanatory. What are the limitations? They do not convey ideas effectively. Sometimes if you have to convey idea, it's always better to go for text matter. And it's not good at depicting trends over a period of time. As I was telling, suppose if you want to show the data of BP over a period of 60 minutes, 5, 10, 15, 20, 25, 30, if you just put it in the form of a table, it will be just numbers. So you will not understand which direction, whether it is decreasing or increasing trend or whatever it is. But if you put the same thing in the line graph, you can see the direction of line and I can understand what's happening to the BP, whether it's going towards a positive side or negative side, isn't it? So coming to the various parts of the table, as I told, this is just a thing. So the top one is the spanner, and this is a column heading, these are row headings, and these are the data cells, and this is the footnote. It's always important to give a footnote whenever you give a table for some of the things what you are mentioning here. You can put a star or something like that and put something like that. So this is the title, which has to be informative and precise. And usually the columns are represented by the rows are represented by the independent variables, whereas the dependent variables are represented by the column headings. And the footnote should contain the explanatory matter, non-standard abbreviations, and data representation statistical details. Common heading for multiple columns and basic rules. It should be self-explanatory, should have a title, should present values in the same number of decimal places in all cells. And for example, if you have, you cannot mention 31.21 in one cell and the next you mention 33.123. It has to be 31.12, 31.33.13, like that only. Okay. And provide all additional information in the table footer when needed. And it has to be inserted into the document only after being mentioned in the text. You have to mention the table. You should mention the table number. You should cite the table number in the result section whenever you are including it in the manuscript. And it should always be preferably numbered by Arabic numerals. Should mandatory mention the number of subjects involved in the analysis. Graphs, it attracts the reader's attention better. Data they depict remains in the reader's memory for a longer time and used for depicting outcomes, relationships, and trends. And various types of graphs include dot graphs, line graphs, bar graphs, etc. It's easily readable. Data points and lines are generally placed and visually balanced and colored, so it is easily faster. It has got a faster grasping capacity. Axis titles are mentioned for better understanding. And there are certain scales. The scales are easily decipherable. And legends to groups helps in identifying different groups. And legends to figure with relevant number. Usually there should be a legend to be mentioned to the figure along with the number, the title, and relevant explanation. If you see, the title of the table is always given above, and the legend to the figure is always given below. That's one of the important things you have to keep in mind. If you see, the trend is so beautifully seen here. If it was in the table, it would just be in the form of numbers, and you will not be able to understand. This gives a better understanding, isn't it? In that, now what are the various components? So you just here I wanted to show one thing. You see the first chart. You see the difference between the two groups. It's quite narrow, isn't it? Though it is statistically significant, it's not shown in the graph that well. But if you see in this, it's quite widened. Now, what is the reason? Is because the selection of appropriate axis scale. If you don't select the appropriate axis scale, you will not be able to show the difference between the two groups. So based on your what do you say, based on your results and it is statistical significance, you can change the scale appropriately and to show the significance in the graph. This is the dot plot used for only small set of data. regression scatter plot, most of the time it is used to understand the trend of the set of data set, whether it's moving in the normal direction or abnormal, or in what direction. And most of the time it represents the independent variable. The independent variable is represented by the y-axis, whereas the x-axis, whereas the dependent variable is always presented on the y-axis. So as the height increases in this graph, you see the height is the independent variable and next circumference. We note that as the height increases, the next circumference also increases, and this regression line shows the trend in the direction of the observation. So the dependent variable increases as the independent variable also increases. That is the understanding of this particular graph. So regression line is if the and direction of regression says whether it's positive or negative correlation. This is a positive correlation. Pie chart represent usually when you want to represent values by percentages. Bar graph is the most common used. So it useful for both categorical as well as quantitative data. Either it can be in the form of horizontal or vertical, and grouped or subdivided in the form of like this. This is subdivided. Vertical graphs are commonly used for all comparisons, and advantage of representing negative data also. Horizontal graph bars are useful when large number of data sets are available. Now, histogram is a specialized kind of a bar plot which shows the underlying frequency distribution set of a continuous data. Basically, this histogram helps us to understand whether the data is skewed distribution or normal distribution. Box line plot is with whiskers. A line graph. This is a special type of a bar graph which has got a line graph. It has got a data trend as a series of data connected by a straight line segments on both axes. It can also compare trends of multiple data sets and can show both positive as well as negative values. This is what I was mentioning. So the standard deviation is the one which is represented in the form of error bars here. It shows both the positive as well as the negative values and the distribution of a value around the central value. This is more effective than bar graphs in displaying small difference between the two groups. This is what I was mentioning about the whiskers, which represents the standard deviation. The disadvantages, it implies more impression than it has. The slanting line appears to represent all the values between the two values, but it's not always. Not useful in representing categorical data. Line graph can never be used for representing the categorical data. Boxes and whiskers plot is one of the most important bar graphs which are used. Generally, this gives all the details of the data set. For example, if you see, it has got a mean, it has got a median, it has got a first and third quartile. It also shows the outliers and also shows the outliers which are not lying within the range of the values. So the entire set of data are summarized and presented in the form of a box. Whisker plots generated on either this is the box and this is the whisker plot. The whisker plots are generated on their side of the blocks and they display variations in the samples of a statistical population. They best suited for non-parametric data. So this is the median, this is the first quartile, this is the third quartile, these outliers, as I told, outliers outside the range, mean. So they can compare multiple data sets from the independent sources, and the advantage is it handles a large amount of data easily and gives a beautiful visual summary of its distribution. The disadvantage is it doesn't reflect the exact values and details of distribution results and not very useful in normally distributed data. ROC curve is a curve generated by a software when one relevant data is fed, and it displaying the range of values under determining the cutoff for a reference range. Most of the times this is usually used for generating, for example, if you are trying to find out a new cutoff value for a particular set of data. Let us say you have collected hypertension at like 100 BP values of hypertensive patients, and you have to define what is the new cutoff. In such situations, you can use this ROC curve. It is mainly used to measure the diagnostics and measure the sensitivity and specificity of the diagnostic test and also compare them at various points on the curve. Area under the curve shows it's a measure of how well a variable may be able to predict the outcome. It quantifies the ability of a test to discriminate between positive and negative outcome. So which one to use? Categorical, you can use either table or bar graph or histogram or pie chart. Categorical ordinal, preferably use a bar graph or histogram or table. Numerical discrete and continuous, again you can use the various numerical discrete, you can use bar graph or histogram. Whereas for a continuous variable, depending upon whether they're normally distributed or non-normally distributed, you can go for line graph, bar graph, histogram, or box and viscous plot, especially for a non-normal distribution or skewed data. Correlation between two continuable variables, you preferably use a scatter plot. You don't go for a table. Correlation between categorical variable, death and discharge from the ICU, etc., against time, you can go for a KM curve or Kaplan-Meier curve. Likewise, diagnostic test, you use ROC curve. For example, Mallampati test, ultrasound test, all those things you can use a ROC curve to generate the sensitivity, specificity, and also the point of success and negative. Thank you. So that completes the statistical class for that completes the basic statistical class.